Today I want to start the mathematics 2 paper code is MT01 for the BTech. This is the second lecture class of the Laplace transformation. Module 32, previous one is the 31. Now start with that. Laplace transformation of the elementary functions. Existence theorem of the Laplace transformation. Existence theorem of the Laplace transformation and properties of the Laplace transformation. That is the two different heading of the theorem. Laplace transformations of ft. That is the function of t equal to sine hyperbolic t and function of t equal to cos hyperbolic t. We want to find out where t is greater than equal to 0. We try to find out that a Laplace transformation of the function if t equal to sine hyperbolic t and if t equal to cos hyperbolic t, where t is greater than equal to 0 because t is starting from 0 and onwards. As per the definition of the Laplace transformation of hyperbolic t equal to 0 to infinity sine hyperbolic t and it is multiplied by e to the power minus st dt. This is from the definition of the Laplace transformation. Now hyperbolic t we can express in terms of e to the power at and e to the power minus at. E to the power at minus e to the power minus at by 2 sine hyperbolic t, and it is multiplied by e to the power minus st dt, where t is greater than equal to 0. We can break it into the two part, this integration. Half we can take outside of the integration, so 0 to infinity e to the power at and e to the power minus st dt minus 0 to infinity e to the power minus at into e to the power minus st dt. This is the Laplace transformation. Now we are considering the convergence of the Laplace transformation. So from that, by the definition of the Laplace transformation, this is the Laplace transformation of e to the power at and this is the Laplace transformation of e to the power minus at. We know the result of this in the previous lecture. We already learned how to find out the Laplace transformation of e to the power at and e to the power minus at. So from that we can write half Laplace transformation of e to the power at minus Laplace transformation of e to the power minus at equal to half of 1 by s minus a minus 1 by s plus a. So by simplifying this, we will get this is a square minus a square and s plus a minus of s and plus a. So from that we will get the 2a. That 2 will be cancelled out. Then we will get the a by a square minus a square. Here a is greater than mod a. That means minus a less than equal to s, s less than equal to a. So Laplace transformation of sine hyperbolic t equal to a by s square minus s square and s greater than equal to mod a. Previously, in the lecture class 31, we already learned the Laplace transformation of sine at and cos at. Similar process we can apply for the cos hyperbolic at. Cos hyperbolic at equal to, by the definition of the Laplace transformation, 0 to infinity cos hyperbolic at now we can write cos hyperbolic at the sum of e to the power at and e to the power minus at. Cos hyperbolic at is equal to e to the power at plus e to the power minus at by 2 and e to the power minus st there. So this is we can write into the two separate terms where t is greater than equal to 0. Half we can take outside of the integration. So e to the power at into e to the power minus st dt is the one part, and 0 to infinity e to the power minus at e to the power minus at is the another part. This is the Laplace transformation. First part is the Laplace transformation of e to the power at. Second part is the Laplace transformation of e to the power minus at. And we are considering that the integration is convergent. That means we will get the finite value of this integration, both the integration. So from that we can write half is outside. So Laplace transformation of e to the power at plus Laplace transformation of e to the power minus at. We know the Laplace transformation of e to the power at is equal to 1 by s minus a, and e to the power minus at is 1 by s plus a. LCM is s square minus a square, s plus a and plus s minus a will be cancelled out, we will get the 2s, and that 2 will be cancelled out, we will get the result s by s square minus a square is greater than equal to mod. So Laplace transformation of cos hyperbolic at equal to s by s square minus a square, and s greater than mod a. That means minus a less than s and s less than a. Table for the Laplace transformation. So basic functions and their transformation is there in the table. When the ft is equal to 1, Laplace transformation of ft is 1 by s, s greater than 0. When ft equal to t, Laplace transformation is 1 by s square and s greater than 0. When it is t to the power n, it is gamma n plus 1 by s to the power n plus 1 and s greater than 0. E to the power at, this is just we apply and learn this result 1 by s minus 1 by s minus a, s greater than a. And cos at we learn in the previous class, lecture class, s by s square plus s square. Sin at, Laplace transformation of sin at is a by s square plus s square. And cos hyperbolic at is s by s square minus s square. Difference is cos hyperbolic at in cos at. Only the sign difference is there, minus. And in this case is greater than mod a. Sin hyperbolic at, difference is this is a by s square plus s square. And here a by s square minus s square. And s greater than mod a. Existence theorem of the Laplace transformation. By the definition of that, I try to explain this. A function ft is said to be piecewise or the sectionally continuous. That means part by part it is continuous, then we can say it is sectionally continuous. That means in some interval the function is continuous, then it is discontinuous, then again in an interval it is continuous. That is the piecewise or the sectionally continuous. On a closed interval, a less than equal to t, t less than equal to b. So in this interval it is continuous. If it be defined on that interval and be such that the interval can be subdivided into a finite number of sub-intervals, in each of which is ft is continuous. In this interval, the function is continuous. We divide this interval into a finite number of sub-intervals where ft is continuous. Second point, a function ft is said to be exponential order as t tends to infinity. When t is increasing and t tends to infinity, if there exists a continuous sigma greater than 0 such that t greater than 0. We also find a time t which is greater than 0, and this t, capital T with respect to the t value, we are choosing some value of the t, small t, that is the capital T greater than 0, and t is running value and which tends to infinity is greater than capital T, such that e to the power minus sigma t and mod of ft is bounded for all t greater than t. So for a certain value of the t which is greater than the capital T, we will get for some capital M that is greater than equal to 0. So mod ft, that is the function mod value, is less than m into e to the power sigma t for t greater than t. So in this case, ft is the bounded above. So considering a function that is t to the power n for our illustration, and n is 1, 2, 3, 4 like that, it is going on. Take sigma as a some fixed positive value. So then limit, we are multiplying e to the power minus 80. See, e to the power minus sigma t, we are multiplying this. Instead of this sigma, we are considering it is the a. Sigma as a fixed positive value, we are considering e to the power minus 80 ft. That is limit e to the power minus 80 t to the power n, because our considering the function ft is the t to the power n. Then the limit t tends to infinity t to the power n by e to the power 80. It is in the infinity by infinity form, because if we take the t tends to infinity, this is also tends to infinity, this is also tends to infinity. So this is the infinity by infinity form. So now we can apply the L'Hospital rule, differentiating this and differentiating this. If we take the n times differentiation, what we will get? N time differentiation we will get from that n into n minus 1 into n minus 2, like that it is going on up to the 1. So from that we will get the factorial n, and from that each and every differentiation we will get a. So after the nth differentiation we will get a to the power n. This is sigma. Instead of using here the a, this should be the sigma, otherwise a we can say. So this should be the a to the power n e to the power 80. Since it is a, so this should be a to the power n by repeated application of the L'Hospital rule. Now if we take t tends to infinity, what we will get? That ultimately we will get this equal to 0. This is free from t, only here is the t. So this is becomes the infinity. So factorial n by infinity will get the is 0. It follows that t to the power n, that is modulus value of t to the power n less than e to the power sigma t. This will be basically the a to the power t. This is e to the power 80 for all t greater than 0. Hence t to the power n is an exponential order as t tends to infinity. So if we consider the function ft equal to t to the power n has the exponential order. A function having the above two properties are called the function of the class A. Existence theorem of the Laplace transformation. Let ft be a piecewise continuous functions in the interval 0 and t, where t is greater than 0, and ft be a exponential order and t tends to infinity for some sigma greater than 0. Then fs, that means Laplace transformation of the function ft, is equal to 0 to infinity ft e to the power minus st dt of ft exists for s greater than sigma. This is from the definition, existence of that, properties of the Laplace transformations. Now we are going to discuss about the properties of the Laplace transformation. First one is the linearity property. If f1t and f2t be two the functions whose Laplace transformation is L f1t and L f2t by the notation exists, then we can write Laplace transformation of a f1t plus b f2t equal to a Laplace transformation of f1t plus b into Laplace transformation of f2t, where a and b are constants. This is we have to prove. So by the definition of the Laplace transformation, we can write from the left hand side Laplace transformation of a f1t plus b f2t equal to, as per definition, 0 to infinity a f1t plus b f2t e to the power minus st dt. Since it is the integration, so we can break it into the two parts, considering a f1t and b f2t. So we can break it into the two parts like that. A is constant, we can take outside of the integration. A 0 to infinity f1t e to the power minus st dt, and here also b we can take it outside of the integration, as b is constant and here a is constant. 0 to infinity f2t e to the power minus st dt. Now, by the definition of Laplace transformation, this part is the Laplace transformation of f1t, and this part, the second part, second term, is the Laplace transformation of f2t. So we can write a into Laplace transformation of f1t plus b into Laplace transformation of f2t. This is proof. So this is the proof of the linearity property. Change of scale property. If Laplace transformation ft equal to fs exists for some s greater than sigma, sigma is greater than 0, then for some constant a not equal to 0, we can write change of scale means that time t is multiplied by a. Instead of ft, if we take the Laplace transformation of f at, then what would be the result of that? When we change of scale, that means t multiplied by a, we will get 1 by a, fs by a. Now we have to prove it by applying the definition. By the definition of Laplace transformation, so Laplace transformation of f at equal to 0 to infinity f at e to the power minus st dt equal to limit. Since it is an improper integration, to find out this, we are taking b is there and b tends to infinity, 0 to b f at e to the power minus st dt. Now take at equal to u. We are taking at equal to u. Then a dt equal to du. And that time changes of the limit. When t is 0, u will be 0. When t is b, so limit, upper limit will be ab. Since our substitution at is equal to u, so t is b, so your u limit will be ab. So limit b tends to infinity, f u e to the power, as per our substitution, t equal to u by a. T equal to, from that we are getting t equal to u by a. So that t will be replaced by u by a. So this is, we can write s by a into u. And from here dt is equal to 1 by a du. From that dt, we are getting 1 by a du, 1 by a du. And 1 by a is the constant that we can take outside of the integration. Now we can changes the limit of this 1 by a 0 to infinity, and this is u and du all are the variable we can changes to the our actual variable t. Anytime in the integration, that variable if we changes to the another variable, it does not matter to changes the value of the integration. U is our the variable that u we can changes to the t. So from that we are getting 0 to infinity ft e to the power minus s by at dt. So by this e to the power minus s by a dt, and this is t. So by the definition, this is 1 by a is outside. So this is the function f s by a. Instead of minus st, here s by at. So this is the Laplace transformation. After that, s will be replaced by s by a. Here, instead of s, there is s by a. So function also, fs also we can write as s by a. It is that 1 by a into f s by a. That is proof. When it is minus st, we are writing this is equal to fs. Since here s by at, so it is at the fs by a. So when t is multiplied by the a, just we replace s is s by a, and before that is multiplied by 1 by a. Laplace transformation of the f t equal to e to the power at and t greater than equal to 0. What would be the answer of that out of this? You think about that and write your answer properly. Shift, fast shifting property. Previously we learned the scale change. Let Laplace transformation of ft equal to fs. If Laplace transformation of ft equal to fs exists for s greater than sigma, sigma greater than 0, then for any constant a, Laplace transformation of e to the power at ft equal to fs minus a for s greater than sigma plus a. We have to show that s will be changes with s minus a. If our ft is multiplied by e to the power at, then our Laplace transformation of ft will be changes, that fs will be changes by s minus. So by the definition of the Laplace transformation, fs is the Laplace transformation of ft, that is by notation Laplace transformation of ft, and by definition is 0 to infinity ft e to the power minus st dt for s greater than sigma and sigma greater than 0. Now again, fs minus a equal to 0 to infinity ft e to the power minus s minus at dt. This is also by the definition. S will be replaced by s minus a. This is s by definition of the Laplace transformation, and that is we are replaced by s minus a. So right hand side s also replaced by s minus a. Here s greater than sigma, sigma greater than 0. Similarly s minus a greater than sigma, sigma greater than 0. So from that we will get s greater than sigma plus a and sigma greater than 0. If I write, so s greater than sigma plus a, if we consider this inequality only, and if we take the separate this 2 1, so 1 if we consider s minus a greater than sigma, so from that we will get s greater than sigma plus a, and from that sigma is greater than 0. So we are writing in the two way. sigma s greater than sigma plus a and sigma greater than 0. Now e to the power minus s minus t s minus at that we can break it into the two parts, e to the power minus st and e to the power at. E to the power at and e to the power minus st. So you can write here e to the power minus st and e to the power at ft dt or s greater than sigma plus a and sigma greater than 0. If we consider this total is a function, so by the definition of Laplace transformation, this is the function. If we consider this is the gt, if we consider this is gt, so Laplace transformation of the gt. So from that we can write Laplace transformation of this function according to the definition. So Laplace transformation of e to the power at ft for s greater than sigma plus a and sigma greater than 0. So we can write it Laplace transform from this side. We can write this. So Laplace transformation of e to the power at ft equal to f s minus a for s greater than sigma plus a, sigma greater than 0. Second shifting property. This is very important. Let us consider Laplace transformation ft equal to fs exists. And we also consider the another function gt, that is the two branch of this. It is defined for t greater than a, it is defined for t less than a. For t greater than a, it is ft minus a, and for t less than a, it is 0. That means function value is 0 when t is less than a, and when t is greater than a, function value is ft minus a. So two function is given. Then Laplace transformation of gt equal to e to the power minus as fs. Fs is the Laplace transformation of ft. And this is ft minus a. Only ft. If we take a equal to 0, we will get ft. That transformation, Laplace transformation of ft is the fs. Now, by definition of the Laplace transformation of gt equal to 0 to infinity gt e to the power minus st dt. Since there is the two branch of the time, one is t greater than a, another is t less than a. So 0 to infinity we can break it into the two parts, 0 to a and a to infinity. So this gt into e to the power st, and this integration we can write into the two parts, 0 to a gt e to the power minus st dt and a to infinity gt e to the power minus st dt. Now when a to infinity t is greater than, so we have this part, t is greater than a, then it is ft minus a, and when t is less than a, that means 0 to a, in this part value of the function gt is the 0. So 0 into e to the power minus st dt plus a to infinity ft minus a e to the power minus st dt. So finally we will get a to infinity ft minus a to the power minus st dt. Now Laplace transformation of gt equal to 0 to infinity gt e to the power minus st dt equal to a to infinity ft minus a e to the power minus st dt. Since it is an improper integration, and for our the processing and simplification, we are considering upper limit is the b, and b tends to infinity. Now if we substitute t minus a equal to capital X or u or v, you can choose anything is there. So t minus a equal to x, so dt equal to dx. Only changes the limit only. When t equal to a, x will be 0, and when t equal to b, x will be b minus a. When t equal to b, x will be b minus a, and when t equal to a, x will be 0. So let us consider t minus a equal to x. So from that we will get, by changing the limit of that, and now we can break it, e to the power minus s, then t, put it here, t equal to x plus a. From that we will get t equal to x plus a. Now we can put it here, minus s into x plus a, and this will be fx dx, because dt equal to dx. So, and this will be changes to this limit, this should be the 0, not the a. This should be 0. By mistake it is there. This should be 0 and b minus a. This should be 0, this should be 0. This 0 to b minus a, and 0 to b minus a, 0 to infinity. Now we can change, the b tends to infinity. Now e to the power minus sa outside of the integration. Now e to the power minus sx fx dx, we can change our the variable as e to the power minus st ft dt. This is 0. 0 to infinity e to the power minus sa. So e to the power minus sa is outside, and this is the Laplace transformation of ft, that means the fs. So from that we will get e to the power minus sa Laplace transformation of ft equal to e to the power minus sa fs. This is the proof. For the illustration, I am taking the example. Let ft equal to cos t minus pi by 3 for t greater than equal to pi by 3, and 0 for t is less than pi by 3. When time is less than pi by 3, function value is 0. When t is greater than pi by 3, function value is cos t minus pi by 3. So here pi by 3 is our the a, this is a, this is a. So by the definition of the Laplace transformation, we know cos, Laplace transformation of cos t. This is we are considering as a cos t. Forget about this part when you considering that. So Laplace transformation of cos t equal to s by s square plus 1 square, because coefficient of t is 1, equal to s by s square plus 1 equal to fs. Say. Now by the shifting property, by the second shifting property, what we will get? Laplace transformation of ft. This here is the ft. So Laplace transformation of ft equal to e to the power a. What is the a? Pi by 3. So e to the power minus pi by 3 s fs. Now what is our fs? This is our the fs. So you can write it e to the power minus pi s by 3 s into s square plus 1. Finally we will get s into e to the power minus pi s by 3 and s square plus 1 by using the second shifting property. Illustration of the linearity property. So first we learned the linearity property. Now I am consider an example for the illustration. Let ft equal to 3 t to the power 5 plus 2 cos cube t minus 5 e to the power minus 3t. Then Laplace transformation of ft is equal to Laplace transformation of the total function 3 t to the power 5 plus 2 cos cube t minus 5 e to the power minus 3. By applying the linearity property, I can take the terms separately. Laplace transformation of 3 t to the power 5 plus Laplace transformation of 2 cos cube t minus is there, so minus Laplace transformation 5 e to the power minus 3t by the linearity property. Now I can take the constant outside of the Laplace transformation. So this is, we can write 3 Laplace transformation of t to the power 5. We know the Laplace transformation of t to the power n. Now Laplace 2 we can take outside. Laplace transformation of cos cube t, this is we have to break it into the coefficient of that. We cannot take in the power. So power is there in a trigonometric function that we have to convert it to the coefficient of that. 2 is outside, and from that we can get 1 by 4 cos 3t minus 3 cos t. And 5 we can take outside, 5 Laplace transformation e to the power minus 3t. So this is again we can break it into the two part. 2 and 1 by 4, that is the half, and from that t, half Laplace transform of cos 3t, and here we will get 3 by 2 Laplace transformation of cos t minus 5 Laplace transformation e to the power minus 3t. For this again we are applying the linearity property. Now 1 by 1 we can put the result. 3 t to the power 5 means factorial 5 by s to the power 6. This power will be 1 more, half Laplace transformation of cos 3t is s by s square plus 3 square. Here cos, so 3 by 2 s by s square plus 1 square minus 5 e to the power minus 3t. That means 1 by s minus minus 3. So from that we can write Laplace transformation of ft equal. From this we will get, and multiplying 360 by s to the power 6 plus s by 2 is that 2 into s square plus 9 plus 3s and 2 into s square plus 1 minus 5 by s plus 3. Let us consider the another example for the change of the scale of the property. Let ft equal to 2 cos square t. Then we want to find out the f3t. If t is replaced by 3t, then what would be our the Laplace transformation? We are considering here ft equal to Laplace transformation of cos square t. Then the Laplace transformation of 2 cos square t, we can write it into the converting to the coefficient of that. So Laplace transformation of 1 plus cos square 2t. Then using the linearity property, we will get Laplace transformation of 1 plus Laplace transformation of cos 2t by the linearity property. So Laplace transformation of 1, we know 1 by s. Laplace transformation of cos 2t, we know s by s square plus 2 square coefficient of t. Then we can write 1 by s plus s by s square plus 4. That is we are considering as a fs, say. Now we want to find out the ft equal to, that means 2 cos square 3t, what would be the Laplace transformation of this? This is the change of scale. That means t is multiplied by 3. Then what would be the Laplace transformation of that? We know Laplace transformation of ft. ft means this new ft equal to 1/3 f s by 3. It should write f3t equal to 1 by 3 f3 s by 3 by the scaling changes property equal to 1 by 3. S will be replaced by s by 3. S will be replaced by s by 3. S will be replaced by s by 3. 2 square is there. So from that, by simplifying this, we will get 1 by 3, and this is 3 by s. S by 3, that means 3 by s plus 1 3 will be is there, and from there 1 by 3, 1, 3 3's cancel out, we will get the 1 3, 3s s square plus 36. So finally we will get 1 by s plus s by s square plus 36. So Laplace transformation of 2 cos square 3t equal to 2s square. By simplifying this will be there, this will be there. That means 2s square 36 and denominator is s into s square plus 36. First shifting property, let ft is equal to sine bt and gt equal to e to the power 80 sine bt. We know Laplace transformation of ft equal to Laplace transformation of sine bt. We know b by s square plus b square. That is we are considering as a f as say s greater than 0. And Laplace transformation of gt equal to Laplace transformation of et into sine bt. It is multiplication of e to the power 80. That means it is equal to fs minus a. So s will be replaced by s minus a by the first shifting property. So b by s will be replaced by s minus a whole square, s minus a whole square plus b square, s greater than. So if we simplify it, we will get the result. Otherwise, we can keep it. Next lecture, we will consider the properties of the Laplace transformation. Another few properties is that we will consider for the next class.